Hey there, Jessica Knight, Research Communications Specialist here. This is the third in our series of introductory videos for Research Day. In this video, Dr. McHugh covers best practices for data visualization. You all know that understanding the basic principles of good data visualization is enormously useful for communicating your science. When it's visualized poorly, it works against us. It can muddy your message, it can create confusion. But when it's done well, visualizations will grab interest and attention, and they can make a point more succinctly and more clearly and with greater impact than words. We have a hands-on follow-up workshop for this topic as well, where you can bring data visualizations that you're working on to get feedback, and that'll be on March 8th. You can find more information on the Research Day website for that. Hope to see you there. Thanks.
As scientists, we learn over time, and we're trained how to create figures and tables and other ways of visualizing our scientific concepts. And depending on who you're trained by or where you are in your career, you may feel very comfortable with this, or you may feel like you need more support in learning. And today I'm really going to focus on what does it mean to choose data visualizations for a more general audience. We often in scientific publications put together beautiful, intricate data visualizations, multi-paneled figures, or graphs with multiple axes or two y-axes, et cetera, to really try to convey the complexity of the data that we generate and to help other scientists along to communications. But the reality of it is this sort of data visualization is part of the art of doing science and being a scientist. And so we have to put a little bit of different lens on it when we are communicating and choosing data visualizations for general audiences. So there's a few rules of thumb. As we know as scientists, the data visualization choice is first dictated by the data type and is second dictated by what it is that we want the audience to learn or see within the data visualization. As we put together visualizations, whether it be for a scientific manuscript or other purpose, we really want our visualizations to tell a story to the audience. The other thing that we want to make sure is that our visualizations support the conclusion or perhaps conclusions you want the audience to draw. And when we're talking about general scientific audiences or general audiences, a rule of thumb that is often suggested and one that I try to use is to have a single takeaway, a main takeaway from each visualization, and at most no more than 1 to 2 additional pieces of information. This isn't about trying to put all the information that you can into a complex figure. It's more about trying to find a way to use a rather straightforward visualization to allow your audience to come to the same conclusion. Other rules that make sense would be to choose commonly recognized visualization types, or if they aren't a commonly recognized visualization type, something that's easily explained. We learn things like box plots and box and whisker plots and violin plots and all kinds of other data visualizations to represent our science to other scientists. But we have to remember when communicating to a general audience, we're going to have to use common or easily explained data visualizations. And if you try to think back to what you learned, perhaps in high school and or college, but really for the general audience, more towards that 8th, 9th grade level, things like violin plots are going to be completely foreign to those audience. And then the final thing to remember is that using aesthetics can really improve the visual experience, and we'll have some slides about that. But to start, I'm just going to run through some of the visualization types. So I throw this slide in here to remember that when we are thinking about visualization in science, we think about the Cartesian coordinates. So basically the X and Y data visualization. And in the X and Y data visualization, we look at a lot of things, linear and nonlinear relationships. But again, for the general audience, your best bet is to really stick with linear relationships. Even graphing something on an exponential scale is going to be really foreign to a lot of people that you may be wanting to target. We also look at some really complicated coordinate systems with things like curved axes or stacked on top of each other, and nested pie charts, for example, spider plots, a lot of really sophisticated ways of visualizing data. And then the other sort of curved axes coordinate systems are maps. When it comes to the general audience, the one that's going to be sort of tangible and easily understood and explained would be maps. So for the most part, I'm going to comment just a little bit about those linear Cartesian coordinates and a little bit about geospatial data and the use of maps for visualization. All right, so the first thing that we're often trying to do is visualization of an amount, and comparing amounts across different categories. So I've put on this slide several different options that we use in science. But the top line is really the bars, either vertical or horizontal, that are a comparison of amounts across categories. Occasionally, we'll have two sets of categories where we'll look at group bars. And in our science, we often get to things that are more complicated, like stacked bars or heat maps or other ways to really look at the relationships. But for the most part, when we're communicating to general audiences, we really want to stay with the options that are on the top column, or sorry, the top row, or the first two options in the bottom row. These are the things that are going to be most familiar and easily recognizable by general audiences. I'll talk a little bit about an instance where we might want to use stacked bars as we go through this, but usually we would hold that back except for very specific types of visualization. Another thing that we want to remember when we're putting together visualization is that arrangement can enhance your understanding and appeal. So to just give an example of what I mean when I say that, I'm going to look at these three different bar charts, which essentially are representing the same data. So the first bar chart is actually a horizontal bar chart of data, and this data happens to be money making from a set of movies. And our options here are to set this bar chart up as it is on the left. But one of the things that you'll notice is that in order for the x-axis labels to actually fit, they have to be put on a horizontal instead of being underneath the bars. To make them not be labeled horizontally, you could spread the bars out, but then you'd make a chart that's very large with a large amount of white space between each bar. So when we're communicating to lay audiences, something that's easier to read as far as the labels would be the chart that's in the middle. In this instance, we see that the labels now are not slanted. They're more accessible and easier to read. However, we're not quite done with looking at the visual appeal of this chart, because as you can see, the bars are not in any particular order. Whereas if you look at the chart that is all the way over to the right side of the screen, you'll see that now we've solved the issue with the labels being difficult to read. And in this instance, we have aligned the bars in a way that is from most gross income down to least. And so it's visually appealing, and it's quite easy for someone to read this, see the differences between bars that are next to each other, and read down now the y-axis labels and get an overall idea very quickly of how these movies fit together. So this is an example of a relatively small tweak between the graph on the left and the one all the way to the right, which improves the way that this is both visually appealing and enhances understanding. Now, something to remember as while we can arrange bars when there are categories that are unique and not related to each other, there is an instance in where arrangement of bars isn't useful. And so if we look at these two bar charts, we're looking at people's age in years on the x-axis versus their median income on the y-axis. As this is represented to the left, we see that it starts with the youngest age, and then each bar has a subsequent increase in age. So while this chart does not have the bars ordered by their height on the y-axis, doing so really makes the data difficult to understand, because if we look at the chart now on the right, we expect age, which is ordinal data that follows each other in categories, to be represented in numerical order. So while the bars might be more visually appealing and they are in ascending or descending order, because each of these categories is related, changing the bars into the descending order actually makes it more difficult for somebody to read and comprehend this graph. So we just looked at a bar chart that is in essence as well, is in essence also a histogram, pardon me, in the last slide. And so with histograms, typically we are visualizing distributions. And for the most part, while there are a lot of ways that we visualize distributions when we're communicating our scientific data, the two that are going to be most familiar to general audiences are either the plain histogram, which is to the left on the top row, or a density plot. We, of course, as scientists, often look at things like cumulative density or quantile plots, or box plots, violin plots, some of the other things that I mentioned before, and also look at stacking of histograms and density plots, including doing things like the ridgeline plot. But again, to the general audience, some of these specialized plot types are going to be a lot more difficult to understand. So for the most part, we want to be sticking to the histogram or the density plot. Thanks, Mike. So when we're doing histograms, the other big thing to remember, and probably the biggest takeaway, is that, again, enhancement or arrangement enhances your understanding and appeal. And then in this instance, these four plots are all of the same data. The difference is that the bin in the histogram is of a different size. So the bars represent from the top left down to the bottom right, each bar represents an increasing number of years as you go from the top, from A to B to C to D. And so we can see that there is some balance in this instance between making the plot visually appealing and fairly clear to understand, and not losing information as we look at the plot. So certainly figure D in the bottom right is, maybe you could argue, the most visually appealing because it ascends and then descends clearly, but we do lose some important information. If we go back to the bins and the amounts in figure C, we can see that if we have this number of bins, we can see which makes sense at a very young age. There are higher counts. Sorry. Another plot, and I throw this one in here to just remind us, this is also another histogram plot. And as scientists, this is looking at the temperature, how it changes over time, over months. So for us, this type of plot we often like. Of course, we could look at the mean temperature, which is the dark lines in this plot, and we can see what is happening over months. As scientists, we often want to know the information that's within the month. So here the box plots are shown to give a range. So while this information is really interesting and adds a lot that can be drawn from this graph, again, a box plot and explaining a box plot and what you are looking at may not be something that's doable in a visualization for a general audience. The next type is visualization of proportions. And something that was interesting that I remember being taught in graduate school, and I've seen in more than one text about visualizing scientific data, is that true scientific data should never use a pie chart. And that it should use a bar chart, which is comparing groups next to each other. And while this is sort of a rule of thumb that we might have been taught in graduate school or taught when we listen to somebody talk about data visualization in science, for the general public, a pie chart is something that's really common and easily recognizable. And so this is an instance where a pie chart can be incredibly useful and can improve understanding. And most people are going to recognize instantly the comparison of proportions. If you take that same data and put it into a bar chart, of course, you are looking at the proportion out of 100, but you lose some of that relative comparison and the ease of understanding that this is really proportion data that you get with a pie chart. Now, the exception to using a pie chart would be this sort of data. So this data is essentially 3 different companies represented in their proportions with 3 different pie charts. And it's very difficult to look from one pie chart to another and make comparisons. And so pie charts were not really designed to have comparisons amongst each other. They're meant to talk about the parts of a single whole. One option would be to actually take this data and look at it in what we call a stacked bar chart. And if you're used to looking at stacked bar charts, you can see that there are differences in the data. But even in this instance, while a stacked bar chart with only 3 bars might be more simple, probably the best thing to do would be actually to pick a grouped bar chart of proportions so you can compare between companies. So it is important to also think about what comparisons are useful. But the biggest take home here too is to remember comparing between 2 pie charts is very difficult on the eye and on our intuitive understanding of the graphic. Probably one of the most common data types and visualizations that we do in our particular work and that we do in science is really the visualization of an X and Y relationship. The 2 most common here are going to be the scatter plot and a line graph. For the most part, these top 2 options are going to be the ones that are most recognizable, although many people are familiar with smooth line graphs or paired data and that demonstrate XY relationships. However, things like bubble charts, which can be really useful to us, are going to be not necessarily easily understood without room for quite a bit of explanation for lay audiences. And then the final type that I want to talk about is at least type of data is geospatial data. And so we typically think about this as map data or map data that has different shading to represent different information. The 2 on the left are going to be really familiar to most audiences. There are more sophisticated types of map data. For example, this cartogram, which is essentially that same data that has taken the map and disrupted the normal map outlines based on the volume of data in each part of the map. So while if you're used to looking at this, it can provide information, it's pretty hard for us to get our handle on. Similarly, taking that same sort of data and putting it into a heat map, while it can be useful if this is your area of expertise, is not really going to be accessible to the general public for quick understanding. The final thing that I guess I want to talk about is not really a type of data, but it's the idea of visualizing uncertainty. And so this is where I think it's really a case-by-case basis. In science, we always want to see the uncertainty around data. We understand probability and statistics, and we work with it all the time. And we understand that it's quite important to have things like error bars and other indicators of how confident we are in the data. In some instances with relatively simple data and the ability to make an explanation for a general audience, using things like error bars can be helpful and give more information. But I would say these need to be used with caution because they're not something that people are necessarily used to seeing, and they may be a more difficult concept depending on the audience and depending on how common your data type or type of explanation is to the general public. The other thing that I want to talk a little bit about is the idea of the aesthetics. So understanding how we can make data prettier or use things such as position, shape, size, color, line widths, line type, etc., to make plots more clear and easily understood. So the first three categories are really position, shape, and color. And so as we're pretty used to looking at scatter plots, for example, we're definitely using position both on the X and Y axis and where that position intercepts to give us information. When we're looking at different categories that are layered on top of something like a scatter plot, for example, adding shape and changing color or both also give us additional information. But it is important to remember that every type of information that you layer on, if you're layering position, shape, and color information all together in a single graph, the graph itself becomes more complicated. The other thing that we use and is incredibly useful is using color as a tool to distinguish. And so in this example, they're looking at states and population growth. This bar chart is organized from largest population growth down to smallest population growth. And they've used a simple 4-region category on top of it. So we can see that the orange bars are from the West, the blue from the South, the green from the Midwest, and the yellow from the Northeast. And so in addition to seeing the actual growth by state, you can actually see that the biggest growth has been in some of the Western states and Southern states, whereas overall, the Midwest and Northeastern states have had the lower amount of growth. So you can make not only state-specific information, but also some more general conclusions from this graph based on the way that the color scheme is used. The other option is to use color to represent data values. And so this would be the most common way that we're used to seeing maps used to tell a data story, where you have essentially a color scale that can either be a single color scale, starting from lightest to darkest, or it could be a scale that starts with one color and moves to another to indicate the density of data in particular geospatial regions. The other option is using color as a tool to highlight. And so in this instance, this is the same chart that we saw a couple slides ago, but the author's point here was they really wanted to highlight what was happening in Texas and Louisiana. So the information that we saw before is still maintained in the background of this graph. It's just been faded visually. So what stands out to us is perhaps the difference between growth in Texas and growth in Louisiana. And depending on the story that you're trying to tell with your data, this can be a really effective tool. It allows people to see the most important point from your data, the biggest conclusion, for example, you want them to draw. As I mentioned earlier, and perhaps here the biggest conclusion is the author of this wants the audience to see that Texas has grown much more quickly in population than Louisiana, But if people are interested in digging down a little bit more, the rest of the data is still present in the chart. And they could make secondary conclusions, such as Nevada's had the highest growth, or that the West and South tend to be growing faster than the Midwest and Northeast.